Okay, can you hear me? Hopefully the connection is going to be better this time. Yeah, I'm going to continue more likely to finish the discussion of the bosonic particle vortex duality that we started in the last lecture, and then we are going to discuss the fractional quantum Hall effect. Since most of people here are high energy theorists, I'm going to present a somewhat less standard way to look at the problem, but it's highlight some interesting symmetries. Okay, so the bosonic particle vortex duality that we have tried to derive last time, only partially successfully. We have some we wrote down a lattice model and the duality transformation, and we can see the final duality coming out. But we have to make an assumption that our lattice model has the continuum limit, that is, there are choices of parameter of the lattice model where the correlation length is larger than the lattice spacing. That is, we are close, we can choose the parameter so that we are close to the second, point of second order phase transition. If we make this assumption, then we have a duality between two field theories. One is the complex scalar field, theory of complex scalar field, with a Lagrangian given by this this model, and then on the other side we have the abelian Higgs model that is given by another theory of a scalar coupled to a gauge field, again also with masses lambda tilde. Sorry, this would be psi square plus 1/4 e square f mu nu square. We said that the duality is supposed to be valid only at the fixed point, infrared fixed point, that which can achieve by tuning m square to the critical value. So m square goes to some critical square. Then we are in between the spontaneous broken and spontaneously unbroken phase. And we have a fixed point where we can think about lambda as some fixed running to a fixed value. So this fixed point is called the Wilson-Fisher fixed point. And in the epsilon expansion, we can see this fixed point rises as a zero of the beta function for lambda. So if we start our theory from some weakly coupled point, some small lambda, it will run to a fixed value lambda. In the epsilon expansion, that is of order epsilon, but in the physical, in our physical world, this is of order 1 because epsilon is 1. So intrinsically, this fixed point is a strongly coupled fixed point. So on this side of the theory, the left side, it's a non-trivial theory. On the other side, we have abelian Higgs model, and we assume this is near the phase transition between Higgs and Coulomb phases. And presumably the physics, if the duality is correct, then the physics at the fixed point and near the fixed point are the same. Okay, so the lattice derivation of this duality is quite useful although it doesn't give us, it doesn't prove this duality. It is a way to map physical quantity from one side to the other. So, for example, suppose you want to compute, you want to ask the question: what is equivalent to the 2-point function of the operator phi on one side, phi x, phi decker y, this green function on this side, for example. So what one can use a lattice for is first to try to understand what it would map to the quantity in our lattice model. So in our lattice model, the phi has a we have only this angle theta. So what it mapped to is basically the expectation value of cosine of theta at x minus cosine theta at y. Point x and point y. And now, when you map to the other side, you have to go through all this duality transformation again. But the crucial place is, we remember when we rewrite this Gaussian, remind you what happened last time. We have this Villain model whose potential is basically sum of this Gaussian. We rewrite this as an integral over some auxiliary field Bij of e2 minus beta ij I, beta ij theta j minus 2 pi and ij, and then minus bij square over 2, some coefficient that I'm not trying to make it correct now. And then when you integrate over d theta, you find that this gives rise to the constraint that sum of Bij with j being neighbor of I is 0. We say that it's some diff b equals 0 condition. So that was done without, for the partition function, that is, we didn't insert any source. And now, if you think about how this cosine, when we insert this cosine into here, what would happen? And you can see that what happened is that the b, this condition, is now no longer true at 2 points, at the point x and y. It becomes like 1 at x and say minus 1 at y point. And so what we have seen is that inserting a particle operator on one side corresponding to having a configuration that breaks the condition divergence of b is equal to 0. Basically here we have like a monopole in 3-dimensional space. So here on one side, inserting a phi operator correspond to inserting some source for like a monopole for the configuration of b. That means that now integral of b, we take integral of b over a small surface surrounding it, surface integral. It's going to be equal to roughly 1 at the point x. And here you annihilate phi again, and then you have another anti-monopole. So this monopole leads to the non-conservation of integral of b d2x taken at the time slice as a function of t. So let me call that some q of b, n. Let me call n of b. This can be a function of t. So if divergence of b is 0, that corresponds to this charge being conserved. But here divergence of b is non-zero. When you insert a source, inserting a source of the monopole correspond to creating a flux of the magnetic field. Is it what I said make sense? From here we find a correspondence. So in this theory of complex scalar field, there is a conserved charge, which is integral d2x phi dagger d 0 phi. That charge is conserved in the complex scalar field. And that charge is mapped to the number of magnetic flux quanta. And if one is careful with the normalization, we find that the duality maps the number of phi quanta to the number of flux quanta on the other side. So what is the current? We write the current. Might be over 2 here, depending on how one find it. This current is going to be correspond. Now I'm going to use just the same notation for the current. They are just mapped to each other. 1 over 2 pi epsilon mu lambda d mu a lambda. That means that the way that if we now couple the theory to a background U1 gauge field, so if we couple the theory to U1 field, say A mu, on one side, on this side we have D mu minus A mu, phi square plus dot dot dot, this mass term and phi 4 term. On the other side, the coupling to the field psi will be very different. On this side, it will be coupled to the A, small a. Right, the coupling of A mu here is A mu times J mu. And this here A mu J mu. And you can think here, this one is also A mu J mu.
So you're not adding dynamical terms for capital A mu, right?
No, A mu is the background.
Background gauge.
Yeah. In principle, you can now couple that to add the dynamical terms, and you have to add it on both sides then. But it's useful to think about A mu as a background field that give us by differentiation through the differentiation of the partition function the current. So then one can see that the current on one side, this current whose conservation law d mu j mu is equal to 0 is the consequence of the equation of motion. On the other side, the conservation of this current doesn't depend on the on equation of motion, just the Bianchi identity.
There's also a conservation law on the right hand side, right? On this.
There is a
abelian.
conservation law on the right hand side. So let's see how this the other map work. So maybe I go to another page. So we have said that the on one side the coupling to electromagnetism. Well, when I say electromagnetism, that means background electromagnetic field, A mu. Coupling to capital A mu has this form, but on the dual side, the coupling is through the Chern-Simons, basically mixing between capital A and little a. The current here, J mu, corresponds to 2 pi epsilon mu lambda, d mu a lambda here. Okay, so now let's look at one equation of motion on the right-hand side. On the right-hand side, we have the following equation of motion. Imagine that you take the action and differentiate with respect to, let me just take A0. Let's do A mu. A mu, then I have this psi data, d mu psi. I'm not sure I get the coefficient right. I think this is right coefficient. Plus 1 over 2 pi epsilon mu lambda d mu a lambda equal to 0. So this one, let me put mu equal to 0, for example. This one would be now the number, the density, basically it's the density of the psi quanta, the U1 psi quanta. But this mu equal to 0 is the magnetic field. So the number of psi quanta is the number of magnetic flux. Okay. Through the equation of motion, one of the equation of motion. And this suggests a way to think about this psi. It's not, it's this psi and phi are completely different fields. They have different coupling to capital A mu. So let's consider here the the Higgs phase. Consider the Higgs phase here, which is from the point of view of condensed matter physics, it's called also superconducting phase. We have basically it's a Ginzburg-Landau model of superconductivity. Okay, so we have a superconductor. Not sure if let me think a little bit. What am I doing here wrong? I want to. Maybe this is not what I want. I want the Higgs phase on the other side. Yeah. Let me I don't know how to do it. Let's forget about this. I think I could do this as well, but let's do the following exercise. Let's consider here the spontaneous symmetry broken phase. This is like a superconductor now, because we couple it to A mu, so that's roughly speaking a superconductor. So we know that if you have a superconductor and we put it in a magnetic field, it will create vortices. And each of the vortex has integral of b over 2 pi through the flux of the magnetic field through one of the vortex is equal to 1. So that allows us to identify this vortex with psi. This vortex is basically psi, because the number of psi is the number of magnetic flux quanta. So that's why the map is called particle vortex duality. The vortex on one side is a particle on the other side. I think if I proceed with what I started to do on this side, and I would also derive the fact that the particle here would be the vortex on the other side. So that's I think that's all we will need to know before going into the next topic. But is there any question for me?
Yes, even without background gauge field capital A, there is still a U1 current on the right hand side, right? For the psi.
So
what is
for the psi?
On the abelian X model, even
the
without
abelian,
even without
the
having
one
the
that is
capital.
gauge.
Yeah, the one that is
gauge.
gauge. Yes.
That current, since this is a gauge related to gauge symmetry, it isn't a conserved charge.
Right.
It is basically this one, and this is just this one.
Right. Yes.
And there is an equation of motion that relates, because now A is dynamical, small a is dynamical field. This current is now simply related to the basically external electromagnetic field. So the
right,
U1 here, the mapping of U1, the U1 here, this U1 is generated by phi, is mapped to a U1 carried by B on the other side. But there is no, the other U1, the U1 with psi is gauged. It's not a global symmetry.
Yes. So, okay. Okay, thanks.
Okay, yeah. Okay, so now let me give a short, give you a short description of big topics in condensed matter physics called the fractional quantum Hall effect. So let us imagine the following model. That's the following physical system. So let us assume that we have a fermion that is confined in 2+1 dimension. So this is confined in the 2-dimensional brane. And the way one can imagine that happen is that suppose I have a theory in which there is a scalar field, some scalar field, it's called phi, whose which has a profile which looks like this, like a king. And we know that if the fermions couple to phi through Yukawa coupling, then this fermion will have a zero mode on the king. Like this, there will be all the fermion outside the kings will be gap, but there is a zero mode on the king. So that's exactly what I want to do. I want to now forget about the gap mode in the bulk, and I have only one zero mode psi. This one is described by an action, which is now d3x. Just the usual action of Dirac fermion in 2+1 dimension. d mu psi, and there is no mass term. It's zero mass. Then gamma mu is 2 by 2 matrix. Okay, so now let us try to couple this fermion to gauge field. And here I'm going to couple that to a three-dimensional gauge field. So I can add here, for example, d mu plus minus IA mu psi on this side, right? It's coupled to the fermion. So it will couple also effectively to the fermion in the on the brane. So it's a two-dimensional 2 plus 1D fermions coupled to, so here for E square integral F mu nu square D 4x. And here it's the now covariant derivative. So does the model make sense? Fermion on a king coupled to, it's a some simplest brane world scenario. But in some sense, it's also similar to what is realized in graphene. And graphene has Dirac fermion coupled to U1 gauge field that propagate in the bulk, except our model here is more symmetric than graphene. It has relativistic invariance. The fermions in graphene propagate with a much lower speed than the speed of light. And also in graphene, there are more than one fermion. Here we assume that there is only one fermion. So one two-component Dirac fermion. Okay. Okay, so this is a perfectly well-defined theory for now, especially if you do E square, assume E square, you assume E square to be much smaller than 1, then it's perturbative. Everything can be calculated, it seems. Even simpler than QED. Some diagrams that diverges in QED doesn't diverge here. But now I'm going to ask the following question. Suppose I turn on the background F12 not equal to 0. Can one quantize the theory of, can one determine the ground state? So to turn on a background of B, we can imagine having current at infinity. To turn on another type of field, giving you a current at infinity, and that gives us a constant magnetic field going through the system. So I'm going to try to convince you this is actually a very non-trivial problem. Even in the limit of weak coupling, E square much less than 1, we don't know the ground state. As theorists, we cannot determine the ground state by doing perturbation theory. So, and the reason is the following. So when you turn on some non-zero background field, in order to quantize the fermionic field, we have to solve the Dirac equation in the background of this field. Okay, so the Dirac equation you can see it's written in somewhat like this form: sigma dot p minus a times psi is equal to a psi. So here I use a certain convention on my Dirac Stigner, so that gamma 0, gamma I is equal to sigma I. So this I runs only 1 and 2. There is no gamma 3, two-dimensional. Ready? So when you write it down, you find this looks something like this. The Hamiltonian is off diagonal, has components 1 z bar, z, psi some psi 1, psi 2 equal e psi 1, e psi 2, while z is a complex coordinate. And dz is something like, write out dz bar to compute, that would be something like d over dz bar. There might be an I here because P is I time derivative. So let me write an I will write just here. So this one like B I is like B divided by 4Z. Yeah, I use the some kind of some gauge for mu. You can choose a gauge for mu. Find dz is equal to dz. I think here might be plus 0.4 z bar. Here it's in the gauge where ax equal half by, ay equal minus half bx. Okay, so here it's one can reduce this to second order. It's a system of two couple differential equation which can be solved, and we can find the spectrum of the Dirac spin, the Dirac spin. So here is the result. Yes, this spectrum. Here I have E, and it becomes discrete. If you have particle in magnetic field, it will move classically. It move in circular orbit. Circular closed orbit means that the energy level is discrete. So we find this equal to 2mb. This one is En equal minus square root of 2mb. The Dirac equation always have negative energy eigenstates. Dirac C, basically. The Dirac C now becomes discrete. But there is a mode here with zero energy, and this mode is given by the following solution. So psi 1, psi 2 is equal to, I think here just psi 1 is 0. But psi 1 satisfied a first order equation, differential equation. The situation is similar to what happened in supersymmetric quantum mechanics. There's one set of modes for which the energy is 0, and it's annihilated by a first order differential operator. Okay, so this one, you can solve this equation. This psi would be equal to E psi 1, right? Psi 1 z bar z times b divided by 4 times z to the n power with any n. In practice, n is limited by the size of the system. One can imagine how to you can look at this square of this wave function. So at n equal to 0, it will be a Gaussian shape, and if we increase n, it will peak at larger and larger z. This is psi 1 z square. So it's some n larger than 1, and at some point the wave function will go beyond the, say if you have a system in the disk with a finite radius, there is a fixed n at which the wave function will be concentrated at the edge of the disk. So, but this can be formalized. The number of this solution is equal to, there are exactly 1 divided by 2 pi integral of b e2x solution. I think there is a theorem, the index theorem, telling us that if I have a fixed, say, manifold, a compact manifold on which there is a magnetic field going through, the number of zero mode of this equation is the number of flux quanta going through it. Okay, and the same for other states. These Landau levels, these are called Landau levels. Okay, and they are also degenerate. Okay, so that is what replaced the usual Dirac C picture. So the usual Dirac C picture, we have mode where energy is a function of P plus P minus P. This is when B equal to 0. And here everything becomes discrete. Now, of course, in the beginning, O.M. Dirac found this negative energy state. He has to have the picture of Dirac C. We know that it corresponds to a certain way to quantize the spinor field. Basically, in the Dirac picture, all these states are field, and so they would we would introduce in the mode decomposition of psi operator A, creating a particle, annihilating antiparticle. I'm not going to go through that. The Dirac picture seems very intuitive. We just fill all the states with negative energy. In the ground state, this declare that to be a ground state, and then this thing is empty. Okay.
So why isn't it continuous as a function of P?
I'm sorry?
The spectrum is discontinuous as a function of P. Is that
there is no P?
No,
in a
as a B.
magnetic field?
No, sorry, I meant
B.
magnetic field. B, yeah.
Yeah.
Why is the
a function
spectrum
of B? It has square root.
No, the spectrum is discontinuous as a function of B. If I take B to 0, like
let's take B to 0, this level become denser.
Okay.
The number of states on each of these, the number of states is become less and less. So it become 1 over 2 pi. Remember, it's 1 over 2 pi integral of B. So there are more and more levels, but less and less states on each level. And so in some sense, going from 0B to finite B, you squeeze out, you group the states into this level. Yeah. Otherwise, they would all have different energy, but now they group together into discrete level.
Yeah, thanks. Yeah.
Mm-hmm. Yeah. The question is now, what happened? What do we do with this state? There is no a priori good prescription to do that. So in fact, if we just try to ignore, just follow the textbook quantization procedure, we would have a ambiguity. So then now we have an ambiguity. That means we have degenerate ground state, which we cannot resolve. So the number of degeneracy is 2 to the power of the number of flux quanta. Right? Number of phi is equal to 1 over 2 pi integral dB. Let me call that. Oh, let me call it NB. Each of these states can be either occupied or unoccupied. And 2 to the power of NB there is a Hilbert space, subspace of the total Hilbert space, whose energy is 0. So that means that this is this problem cannot be solved. The interaction, this coupling to electromagnetic field. Now these electrons have Coulomb interaction, electromagnetic interaction with each other. Presumably single out one ground state. We will need interaction to determine the ground state. But a priori, we don't know the ground state. Okay, so any question so far? So let's try to understand what is the, so here we have an infinite 2 to the n degenerate state that are degenerate, right? And I want to understand, if I turn on interaction, what is the scale of all these states now will have, the picture will be more like this. The degeneracy is going to be lifted. Let us try to estimate the energy, the spread of the energy between these states. So for that, the spread of the energy, let me call that delta E. Delta E is, roughly speaking, this delta E can be expected to be the strength of the Coulomb interaction at E squared over R. And R is the typical distance between the electrons, the particles, my particle, but there are the number of these particles. So these particles that are located on this Landau level, there are roughly n5 of them. Okay, n5, and the yes, the density, its density is, oh sorry, NB divided by the area, but NB is integral of B, 1 over 2 pi, integral of BDS, which is B over 2 pi times the area. And so this density of this particle is B. Distance between particle, neighboring particle, is 1 over square root of B. And so this one is E squared times square root of B. That's the amount of spread that we expect to have. That estimate, since it is just an order of magnitude estimate, it's obviously we cannot make a calculation of the prefactor. Okay, so now let's recall that previously we found that the distance from the 0 Landau level to the first Landau level, 0 energy, is square root of 2b. This one is much less than square root of 2b. If E squared is much less than 1. And so everything that we have here is, all the non-trivial physics happens in the single Landau level. So this one Landau level determines everything non-trivial. That is because this energy scale of the other Landau level are so high compared to the interaction between the S electrons. This electron here, the they interact with each other with certain energy scale, but this energy scale is still small compared to the energy needed to move one particle to the next Landau level to create like a particle hole pair. When one particle is on one Landau level, the other is, the hole is in one Landau level, the particle is on the other Landau level. And so basically they try to rearrange themselves within this Landau level, and then the interaction lifts the degeneracy, and we hopefully get the ground state, some non-trivial ground state. So this limit is called in the condensed matter physics the lowest Landau level limit. In our case, it's better to call it a single Landau level limit, in which one single zero mode determines the all the non-perturbative physics happen within the sector of the zero mode of the Dirac equation. So any questions? So far?
Can I ask a question?
Yeah, sure.
I missed how you got the radius to be proportional to 1 over the square root of b.
Okay, so here I'm saying the following. I want, this is this delta E is basically I imagine my system to be a collection of electrons, right? And then R is the distance between two neighboring electrons, the neighboring psi. Okay, so now when I try to estimate that, I have a situation when you have this zero mode, and then a lot of few Landau level. So in principle, the number of electrons is infinite, right? If I naively calculate the whole Dirac sea of negative energy levels are few. But as Dirac told us, these have to be regularized. We have to count this as we have to basically add a background to compensate for this energy. So the non-trivial part of the electrons are all those here on the zero Landau level. Now, how many of these electrons? So the number of these electrons, we know this is NB. The number of state is NB. It's not the number of electrons, but say half of them are filled with electron and half are empty. It's most non-trivial case. So there is 1/2 NB of them. Since 1/2 NB is B divided by 4 pi times the area. So the density of electron is B divided by 4 pi. So now we have the density. That means that the distance is just 1 divided by square root of density. 1 divided by square root of density. And that is 1 over square root of B.
I see.
Yeah.
Okay, thank you.
Yeah. Okay, so here is the situation. One single Landau limit determine everything. It's a non-trivial problem. But, the Hilbert space is much smaller than the original Hilbert space of quantum field theory. So the problem in this sense is simpler than typical quantum field theory, but it's actually more difficult because we don't have the starting point. There's no perturbative starting point in this problem. So this is one of the rare, I think, cases in physics where actually the insight from experiments is almost indispensable. I'm not sure if we can solve this problem without the insight from experiment. So in experiments, people did not realize literally our model, but what they can do is to realize non-relativistic fermions in B field. So the problem is somewhat different because non-relativistic fermion in B field has a different spectrum. In the magnetic field, it's not, doesn't goes to minus infinity, but this is equal to 0. This is E equal like B divided by M and plus a half. But they can achieve the they can also achieve the lowest Landau level limit. That's when the interaction energy is much less than the distance to the next Landau level. So everything is again happen on a single Landau level. And they can achieve they can then put the system in, study the system in the lab, basically realize non-relativistic electron with all the physics happen in one single Landau level, have less electrons than the degeneracy, and then watch what happens. So let me denote one parameter that's going to be important. Mu is the number of electrons divided by the degeneracy of the Landau level, MB. So it's MB again is 1/2 pi B. And so this is the density of electron divided by B/2 pi. And if mu is less than 1, between 0 and 1, we have the so-called fractional quantum Hall effect, which is everything is happen on the single Landau level. Degenerate ground state in the non-interacting case. So the experimental result that we will need is the following. So if mu is equal to 1/2, the system is gapless. And it is a gapless Fermi liquid. When mu is equal n divided by 2n plus n minus 1, the system is gap. N goes from 1, 2, 3, etc. So this 1/3, 2/5, 3/7 for the choice plus of the sign, and then 2/3, 3/5, 4/7 for the minus sign. So whatever the theory that we need to build for this model, we have to satisfy this, to at least reproduce, explain this qualitative feature of the nature of the ground state. Okay, so this Fermi liquid, let me answer. This Fermi liquid is a state where I have a Fermi sphere and all excitations, quasi-particle excitation, are the excitation near at the Fermi momentum. And the density of the fermion, it's known also that the Fermi momentum is equal to the Fermi momentum of electron as if the B field is 0. So if I have, so here we are talking about some system of electron in a high magnetic field, but at half filling, the ground state is a Fermi liquid of something whose Fermi momentum is equal to the Fermi momentum of the electron if the magnetic field was 0. So that is Kf is equal square root of 4 pi times the number of electrons. So if you work out the connection between density and Fermi momentum, that's okay. So I'm not going to describe how they determine this Fermi momentum. There's very ingenious experimental method to do that. Based on observing certain resonances in the transport. Okay, but now we are going to try to write down some theory that would reproduce this experimental result. So the theory. So on the electron side, we try to, so I'm not going, yeah, so I'm going to present you certain final result that we will see that it gives us all the experimental consequences that we want. The theory is that there is certain fermionic version of particle vortex duality that map the theory of electrons, for which the Lagrangian is known, which the action is known, 3D. So psi mu, d mu minus a mu psi, plus like f mu mu square in 4D. Into a theory of another field. Let me call that, so let me call that psi E. This is electrons, and this one is psi without E. Psi gamma mu d mu minus IA mu psi minus 1/4 pi epsilon mu lambda mu lambda plus the 4D mu square minus see it's exactly the form of the duality is almost exactly the same as the form of duality in scalar case, except for one thing that's going to be that is different is the coefficient. This coefficient here in the bosonic case, it used to be 1/2 pi. Here we have 1/4 pi. And one way to get that is just to see whether we reproduce all the experimental results. So it's duality between a fermion and a fermion in the same form as the duality between a particle and vortex. Okay, so now let's see what the duality can tell us about the ground state. Okay, so now the ground state of this theory, we want to find the ground state of this theory in background B field, B equal E1A2 minus D2A1. It's not equal to 0.
Is there still a dynamical term for little a on the right hand side?
Right, yeah, I can write minus 4,
Okay.
some kind of E tilde F mu square E3x. That's what you have to assume. But I'm going to, it's actually, there is a subtle point that I'm going to defer to later. Going to assume now that I have run to the infrared. And in the infrared, E square is infinity. Right. In the E tilde is a three-dimensional. It's different from the Maxwell term for the capital A that's supposed to be in 4 dimensions. This is a gauge field, emergent gauge field that emerges only on our brain, and so has 3-dimensional dynamics, and it's relevant. And so I'm going to assume that I have run to the infrared far enough so that I put that to infinity. So that's 0. Okay, so now if I do that, if I have done that, then the magnetic field here is 0. Okay, so what does it correspond to in this case? On the other side. On the other side, there is an equation of motion. Here S over dA0 is equal to 0. And that means that we have psi, so here psi bar gamma 0, psi minus b over 4 pi is equal to 0. So that means that this is the number of psi, the density of psi. The density of psi quanta is equal to b over 4 pi. So I have that many psi quanta coupled to my a mu field. Now, what is a mu? Does a mu, small a mu, has expectation value? Or in order to formulate the problem, gauge invariant way, we can ask, what is the expectation value of this little b? So here if I compute the charge density, but the physical charge density, that is ds over the capital A0, I find that is minus b over 4 pi. Okay, so now here I have to match that with the density on the other side. So the other side, I imagine some field under level, this E equal to 0. I'm going to fill this symmetrically. So have half field Landau level. And half field Landau level, I expect that correspond to the expectation value of the current equal to 0. This can be formalized by looking at the discrete symmetry of the Dirac equation. So this state is invariant under CT or PT symmetry. If I have CP or CT, if I declare that my vacuum have to be unbroken under a combination of C and T, combination of P and T, then the charge density is 0. I cannot use separately T or P or C, because I have a magnetic field which flip sign under each of these discrete transformation. I combine them, then the problem has the symmetry. If all the discrete symmetry of the original theory is not broken by the ground state, then the charge density has to be 0, or this level is half field. So if J equal to 0, that means it's B equal to 0. So expectation of B is 0. Expectation of B equal to 0 means that we have basically a finite number of these fermions, and they don't have to run in circle. they run in straight line, and then they are just like usual fermion, and they fill a Fermi surface. In momentum space kx, ky. Okay, here I have used some physical insight also started from Landau. Landau noticed that if I turn on interaction between fermion, the Fermi surface is still sharp. The stability of the Fermi surface persists for finite interaction between the fermions. So here we assume that although these fermions interact with each other through the gauge field, the Fermi surface still intact. Right. So basically, here we have explained one of the puzzling feature of the fractional quantum Hall effect, namely, if we have half field Landau level, the ground state has excitation. Ground state is a Fermi liquid with quasi-particle excitation that do not fill the electric field at all. These are the psi quanta. You can actually see in the experiment in which people see semi-classical trajectory of some quasi-particle that almost doesn't bend itself when while in the when the magnetic field is very high. Okay, so that's one thing. So that also require this coefficient to be 4 pi. If we have 2 pi, then there is no the radius of the Fermi surface will be different from what was found in experiment. Okay, so let's do one more exercise and then we are done today. Let's try to explain what happened when the Landau level is filled. So filled to filling factor n divided by 2n plus 1. So that includes 1/3, 2/5, etc. So experimentally, we found this state to be gapped. We want to understand how this can be explained through this duality. So this is 1/2 minus 1 divided by 2n plus 1. So we have shifted the number of electrons. The density of electrons is now not equal to 0, but we have taken away this fraction of the total number of states on the lowest Landau level. That is b over 2 pi per unit area. So this number of electrons is this J0, right? And J0, okay. J0, we know that, so it is minus. Okay, so because of a minus, this is J0 here, we know is equal to B divided by minus B divided by 4 pi. And that means B is equal to what? To this thing times 4 pi, 1 divided by 2n plus 1 times B. So we have the situation, the following situation. We have this psi particle with density equal B over 4 pi, living in a finite magnetic field. And now you can, I can leave this as an exercise. You can check that this, if you look at the degeneracy of the Landau level, you can convince yourself this is the way to to have this particle is to fill up all the state up to certain Landau level n. So this is E equal to 0. And since you fill up an integer number of Landau level, that system, that state has a gap. Basically, you need to count how many states are there in each Landau level, but you have to count only 1/2 of the E equal to 0 Landau level. Okay, you start from a half field level here, which is supposed to have 0 density of this psi particle, and then filled up, and one can see that this state correspond to field integer number of Landau level, and that explains the appearance of a gap. So everything works out nicely, at least at the qualitative level. Okay, so let me stop here, and next time we are going to see to dig more deeply into this duality. I'm going to show you these two duality. We have this bosonic plus this fermionic duality. The fermionic duality is the one that we have used to explain certain features of the fractional quantum Hall effect. They can all be derived from a certain seed duality. And that's going to be even more speculative than what you have seen so far.
Okay, thanks a lot. Are there some quick questions?
Can you explain again how this thing is gapped? Like, I didn't quite understand why having a non-zero value for little b implies that there is a gap.
So non-zero value for little b means that the states are discrete. So if we have a finite chemical potential that lies between two Landau level, what happens is all the lower Landau level, all the states with energy less than the chemical potential are filled. The upper state here are empty. In order to excite anything, you have to move a psi particle from one Landau level, put it on the higher Landau level. That costs energy.
Okay. Yeah.
Yeah.
Thanks.
Yeah. So that energy, that energy is. You can see also this energy should go down with this capital N, and experimentally that also observed.
Yeah. Okay. Yeah. Thanks.
Yeah.
Other questions? So I have a question actually. At various, I guess, to understand these theories experimentally, you often need to introduce disorder, but that doesn't seem to play a role in the statement of these dualities. So at what level should so where should I think about having to introduce disorder?
In order to explain these plateaus in, say, when we present experimental evidence of fractional quantum Hall state, we have this certain plateau as a function of nu. In order to explain the emergence of the plateaus, we have to invoke disorder. But in order to explain the gap, we don't. So the existence of the, it seems that the gap, the existence of the gap plus disorder are required for the stability of this plateau. But you can discuss the gap without disorder. The gap actually is seen in numerical simulations of particle on the lowest Landau level. So we are pretty sure that the existence of the gap doesn't require disorder.
Okay, thank you. Yeah. Are there any other questions? Quick questions? Yes.
I cannot hear you.
Can't hear you. And in India, we can't hear you. You're unmuted, but we can't hear you. So try again, or maybe type.
Or maybe you can
your
type.
question into the chat.
Yeah, we don't know much about this this duality, right? So this, if this duality is valid as written here, that means that this theory, the fermionic theory, this fermionic theory actually doesn't, there is no psi to the fourth interaction. It would be irrelevant. So this theory is basically a free theory. It's a duality between a free theory and a theory that seems to be interacting. So if this duality is valid in the strongest sense, we take this fermion coupled to a gauge field, run it through the infrared. It has to run because the coupling constant is E tilde here is relevant. We run it all the way to the infrared and we should see a theory of free fermions. There is much less. I don't think there is conclusive evidence for that statement yet.
Okay. Are there any other quick questions? Okay. Let's thank Damson again.